Welcome to this lecture on synchronous machines. We have been discussing, as I told you, that synchronous machine are of two types. One is cylindrical rotor synchronous machine, cylindrical rotor, or uniform gap, or it is also called non-salient pole type rotor structure, where field winding is housed. Based on that, it is classified, and the other is salient pole type, salient pole synchronous machine. Now, the analysis of these two kinds of machine is different. Also, it will be reflected in their phasor diagrams. Now, you recall that in cylindrical machine, if you have understood the cylindrical machine synchronous reactance correctly, then there will be not much of a difference. Recall that in case of cylindrical rotor type synchronous machine, where air gap is uniform, then the phasor diagram was drawn like that okay, if this is your phi f, then under no load condition this will be your E f, 90 degree lagging. All are rotating with synchronous speed in this direction. How this phi f was obtained? Because phi f is the decided by I f, the rotor field current. This was the thing. But when this synchronous machine will be loaded, then I told that suppose it is a lagging power factor load, then I a will be here, I a will be here, armature current, lagging power factor. This angle is called internal power factor angle, usually denoted by psi, but whatever it is, this is suppose lagging I a. And once this I a is obtained, then I will say under no load condition, it was only phi f existing in the air gap, but when also the armature will carry current, balanced three phase current I a, armature MMF will also come along this. And to find out the induced voltage now, you and also phi r will, phi a will be along this direction, and these two together will decide the resultant flux here phi r, this is not rotor, resultant flux, and then induced voltage will be somewhere else here. And then I showed that this change in induced voltage from E f to E r can be considered to be a reactance voltage drop called I x a r. And from here, if you subtract the leakage impedance drop, you get the terminal voltage. That was the argument. Now, in case of cylindrical type machine, this x a r was constant, armature reaction reactance, and recall x s was then x a r plus x a l, and then we told that okay, look here, you need not calculate phi r. So far as the modeling of the machine is concerned, you simply do like this, an impedance R A j x s, x s is x a r plus x a l and so on, and this is your terminal voltage, generator mode, this is the thing. So, one reactance could do that. Now, why one reactance can do? Because it the direction of M A is decided by the power factor angle of the machine at which it is operating. It could be anywhere, here, here, leading power factor, it will be there, and so on. But only so armature MMF, when armature carries current, will be can be in any place in the air gap. But we have the advantage that air gap is uniform. So, to calculate phi a, you have to divide this M A by a constant reluctance. So, everything was fine. Now, let us see in case of a synchronous machine, where the situation is like this. I will not draw, because last time I drew. The stator houses 3-phase winding and it is salient pole structure. So, air gap will be minimum along the salient pole axis, field axis, and air gap will be maximum when it is along this. And when your armature winding will carry current, as I told you, armature MMF could be anywhere in space. As a power factor at which the machine is operating will go on changing, the position of MA, armature MMF, will also go on changing. As it goes on changing, air gap seen by the armature MMF will be also changing. Therefore, it is very difficult, and to calculate the flux for different position, you have to divide this MMF by reluctance, which is position dependent. Therefore, it is very difficult to model what to do with this. Is it, then I have to calculate wherever it is, I will calculate precisely the reluctance, divide it by it, get the armature flux. It is not really like that. Blondel proposed an elegant method. He told that okay, if this is your only this field winding I am drawing, suppose this is the armature rotor field salient pole type. If you draw like this, I am not drawing the stator part. Okay. The field winding will be here and it will have some cross dot. So, field axis will be this one, there is no doubt about it, and your phi f will be along this line, is not, phi f will be along this line. And not only that, if this is phi f, the no load induced voltage will be at right angles, that we have seen. E f axis will lie along this line, is not 90 degree, that is what, that if this is phi f, 90 degree behind E f is there. Now, the argument is this axis is there, and I just call this axis to be, give some name, T axis, and this line, this red line I call Q axis, quadrature axis. These are at 90 degrees, and along this axis air gap is minimum, and along this axis air gap is maximum. Now, your armature MMF or armature current which produces MMF could be anywhere in this space. For example, your MA is here, and in the phasor diagram this is also IA, like this. So, the interesting thing is suggested is this, okay, the problem is this IA will be, can be here, can be there, depending on power factor angle and so on. Therefore, reluctances are varying. So, why not break up this armature current into its D and Q axis? For example, this IA can be thought of phasor sum of these two currents, ID and IQ. No matter where the IA will be, I can always find out its component along the direct and quadrature axis. For example, this IA becomes ID. So, IA can be thought of, you can replace this IA thinking that okay, there are two currents like this exists in the armature. And then the argument is, if this is ID, then MD will be also along this line and MQ will be along this line. So, because of ID, therefore, the change in voltage drop can be taken as we have taken here. So, I will say that under no load condition when I A was 0, if this was your E f, now I A is here, suppose I A is here, and this E f axis is q axis. So, I will draw a line here, that is the d axis, and I will divide this current as I d and I q, these components, and then I will forget about I A. I will replace this armature current as two components, I d and I q. Then I will say, okay, from because of I d there will be a change in voltage, and because of I d there will be a armature reaction flux x a r d plus x a l. This will be some direct axis reactance, and x q is equal to x a r q plus x a l. Mind you, the leakage reactance is not affected, because leakage reactance path will be this armature conductor, and it will complete its path through air gap. Okay. So, leakage reactance remains x a l. Therefore, you have to simply define, instead of a synchronous single synchronous reactance x s, as we did in case of a cylindrical rotor machine, it will be then two reactances. What is the benefit of decomposing the current? Because I know along the d axis the reluctance is constant. Along the q axis, although maximum air gap, but reluctance along that axis is also constant. Therefore, you have to deal with now two constant armature reaction reactances x a r d, x a r q, in the same way as we did in case of synchronous cylindrical type synchronous machine. So, with this understanding, then I can proceed to draw the phasor diagram of this machine rather easily. The crux of the matter is air gap is varying, reluctance is position dependent. I must calculate armature flux to add to the no load flux phi f to get the resultant flux, hence the resultant induced voltage. But this is difficult to carry out, as reluctance in different positions will be different. So, the suggestion is armature MMF, which is because of stator armature current, its distribution, etc., we have seen. So, armature current can be always thought of having two components, one is M d, another is M q. This two components, this is M q, and then M d is there. So, I will be able to calculate phi d. M q is known, I will be able to calculate phi q resultant flux. But then I will simply say that this M d is produced by an equivalent armature current flowing along this direction, direct axis I d, and another current I q produces M q. Then rest of the things I know what to do. Instead of a single current there, now for I d and I q, I have to define two reactances, and I will add them up to get the resultant force. See what I am doing. Suppose let us assume, so how to draw phasor diagram, and it must be understood that x d will be always higher, maybe much higher than x q, because of what? Because flux produced along the d axis will be more for a given current, because reluctance is minimum along d axis. So, x d flux linkage will be more compared to q axis for the same current. Therefore, x d is always greater than x q. Now, let us see how really it will help me to first draw the phasor diagram, then we will try to attempt to calculate the or get the expression for power, reactive power, this that. First, please listen carefully what I am doing. Suppose I have assumed it is generator mode, and suppose it is operating at lagging power factor. Is that clear? Terminal voltage is V per phase, terminal voltage per phase is V, and excitation or no load voltage or excitation voltage is equal to per phase is EF. This is the thing. Armature current is IA. This can be measured, that is this is the machine, salient pole machine. Okay. This is the salient pole machine. This is the rotor, windings are here, and this fellow is running. So, armature current is this current, terminal voltage is, if it is star connected, per phase voltage V root 3 V, that is the thing, and it is delivering IA current, balanced current. So, excitation no load voltage IA is the armature current, and power factor angle is equal to theta, and this is the thing. So, this is your EF or V, let me start with V. So, to V, if I go on adding the drops, resistance drop, then reactance drop, I must get my EF. What is known to me is these two things. This you please be with me for every statement I do here, what exactly I am doing. So, these are the things which I can measure at the terminal. What is the per phase voltage, what current it is delivering, and at what power factor angle. How do I know power factor angle? Connect some wattmeter, how much power it is delivering, VI is known. So, theta is known. These are precisely known to me. Now, I have to add the drops. Now, in case of cylindrical machine, it was so simple, IA plus VIA plus VIA JXS, so one reactance. But here I cannot do it, because your armature MMF will be here and its position can be anywhere, reluctances will be different, the same old story. Therefore, I cannot do anything. I cannot at least think of a single reactance which can be used to at the drop across which can be used to compute EF. Instead, what we will be doing, I will break up this current in the D and Q axis. Now, the big question is, where is D, where is Q axis here? I do not know anything, it looks like, but only one thing I know, it is a generator operation. Therefore, EF axis must be above it, is not? EF axis must be above V. That is why it is generating. In generator mode, EF will be always ahead of V, okay, and this angle is delta. Of course, delta is not known now. So Q axis, which is along EF axis, will be above it, I know. I just draw it. Suppose it is known, suppose to begin with. Then what I will do is this, listen carefully. I will draw a line perpendicular to this here. This is at right angles. You draw a line and you say this will be D axis, means where the poles are there, understood. This is the d axis along this line. Okay. If this is d axis, then what will be done is this armature current, I will drop a perpendicular from the tip on the d axis, and I will say this is your I d. M d will be created here, always a constant reluctance, and this will be your M q or I q. This will be the thing. Is that clear? Then what I am going to do is this, I will add to V a voltage J I d x d. I d is here, its drop 90 degree ahead. So, this drop will be parallel to q axis J I d x d. Okay. And of course, I have neglected here R A. Okay. Suppose R A is 0. Then I know this much, E f should be generator mode V plus J I d x d plus J I q x q and plus I A R A. I will take into account. I have assumed R A to be 0. So, only J I d x d, and then I have to add J I q x q. I q is along this. So, J I q x q will be like this. So, you add this to J I q x q, and then this will be your E f. That is what you have to do. Okay. So, V plus J I d x d plus J I q x q will give you the excitation voltage. So, I am doing once again, and this time I will include R A also. So, what I am doing, informations which will be available to you or measurable quantities is I A, power factor angle theta at which that machine is operating, and the terminal voltage. So, this time, so in case of generator, you first draw V, that is there, and this I A I can draw with confidence, no problem, and this is the power factor angle theta. The next question is, okay, this is I A, where is q and d axis? Okay, I am not certain, but I am sure about one thing, your E f must lie above this. So, suppose this is your q axis then, because E f will lie here and this E f line is your q axis line. And then wherever E f will be, I am not knowing till now, but I am sure about this thing, this angle will be some delta, angle between E f and terminal voltage. Then I am drawing a line perpendicular to this, and I will say this is your d axis, d axis. Okay. Once I know this, I will be able to break up this current into, drop a perpendicular here, this will be your I d and this will be your I q along these two axes, so that the corresponding MMFs will always see constant reluctance along d and constant reluctance along q. Then your V terminal voltage to this, if you add I A R A, of course, I A R A remains I A R A. So, I will add I A R A here. There is no dq axis, you need not break it up. Of course, you can do ID, RD and so on. IARA you sketch. Then to this you add J ID XD. ID is a J ID XD, and then to this you add J IQ XQ, and you will get EF. And this will be the thing, phasor diagram is over. But from this phasor diagram, one should not say that one can draw a equivalent circuit as we did in case of synchronous machine as EF, cylindrical machine, a single impedance ZS and V is not for cylindrical machine. This was the phasor diagram, so simple. But here this between V and EF I cannot put a single reactance to get this this sort of equivalent circuit. In fact, we will not try to get this sort of equivalent circuit at all, it will not be needed. You have to take ID IQ separately and get this, and XD is always greater than XQ, maybe much higher compared to XQ. RA is of course very small, but nonetheless this is the phasor diagram. So, this angle between EF and IA is called the internal power factor angle psi. It is usually denoted internal power factor angle. If this is psi, this is also psi. So, you can see from this triangle that ID will be nothing but magnitude of IA into sin psi, and IQ will be is equal to IA cosine psi, where this is psi is nothing but delta plus theta in this particular generator mode of operation lagging power factor, it is like this. So, this can be written as sin delta plus theta, and this can be written as IA cosine delta plus theta. So, these are the relations we have got. But still if the phasor diagram is completed, you have gone up to EF, then I can do something this way, that way, I will write down the equations. But the big question is, I do not know the value of delta, because what I know V terminal voltage, I know IA, I can measure with an ammeter, I can measure with voltmeter terminal, and power factor angle I can estimate by connecting and wattmeter. I do not have any knowledge of delta. So, we will take up in the next class how to estimate delta and precisely get the q axis, then only you can do all these things. Unless delta is known, how can you calculate ID and IQ? Hope you are following me. So, we will continue with this. Thank you.